for coming. My name is Lee Orff. I'm a scientist with SIMS downstairs. Kelton Halbert is going to give a talk today. He's working with Kelton. He's my PhD student on one of my grants. Kelton received his Bachelor of Science degree from the University of Oklahoma in 2017. He's currently in the beginning of his third year as a PhD student here. Kelton enjoys storm chasing, fixed prize, photography. Those two things kind of go hand in hand, it seems. Coding, he's a very good coder, and he likes to learn musical instruments. He's been teaching himself the fiddle, the banjo, and other things like that. Kelton recently presented some of his science at the Cyclone Workshop in Germany, and he's also presented at the Blue Water Symposium earlier in the spring. Kelton is going to be talking about high-resolution simulations of supercell thunderstorms that form long-lived tornadoes, and this is sort of a snapshot of where he is in one aspect of his work. So, Kelton, I will let you take it from here. Thank you very much.
Yeah, so this is, as Lee said, this is in the broader context of my PhD, looking at these simulations that lead to violent supercell tornadoes, specifically long-lived ones. But this really is a dive into something that started in Anker's boundary layer class of looking at boundary conditions and turbulence in these simulations and how they impact the generation of horizontal vorticity. So just saying that this is a smaller, narrower focus on the problem of boundaries and turbulence in these simulations, understanding their problems before then going on to make bigger conclusions about actual dynamical processes in the storm. And to motivate that a little bit, I'm going to go ahead and show you some results and why we care about the boundary condition turbulence closure. This is the near updrafted, spatially averaged time height cross section of some updraft fields. So on the left I have DW-DZ, which when you assume incompressibility would be your stretching of your vorticity, but this is a fully compressible simulation, so this is just an easier way to show that kind of stretching or acceleration that can happen in the lowest levels. And then on the right is the time height of the updraft field itself. So what you really see is an increasing amount of stretching and acceleration in the lowest, really 1 kilometer of the simulation leading up to tornadogenesis, which is what the black line is. Actually independently chosen by Austin Dixon as tornadogenesis before I made this figure, so it's actually an accident that they match up like that, which is pretty encouraging. And then just to show that it's really the descending of the updraft that's resulting in that DW-DZ changing. You can see the slope of the ice attacks down as you get closer to tornadogenesis, and this is all happening really in the lowest kilometer to 500 meters. So this is the same idea of the plot. They're showing the streamwise vorticity magnitude averaged inside an area around the updraft. And what you see is an increase in the depth of streamwise vorticity being ingested by the storm, and then the magnitude increases after the tornado is already developed and intensifying into the maintenance phase. And again, the left side is in kilometers, and this is all happening in a very shallow layer near the ground, which is why we should care about the boundary condition. And to illustrate that further, these are some selected parcels that enter the low-level mesocyclone, and they come from a layer really about 100 meters to 200 meters from the ground. Boundary conditions in these simulations and turbulence closure are potential weakness to the analysis if you don't understand how it's impacting the generation of the horizontal vorticity being ingested by the updraft. So this is kind of a dive into what's actually happening at that lower boundary. But before going into that, I just wanted to go and give a brief overview and history of tornado forecasting and modeling in the context of large eddy simulations. This is not meant to be an exhaustive review of every piece of work done on tornadoes, but kind of provide the background for the context in which these results stand today. So to start off with that, it cannot be understated or overstated the importance of the first tornado forecast in setting off the science of the modeling and the theory, because if it weren't for what essentially amounted to an accident from the Tinker Air Force Base tornado forecast, we would not have tornado science the way we do today. And that was because of Lieutenant Colonel Ernest J. Fallbush and Captain Robert C. Miller, and effectively a tornado hit Tinker Air Force Base and caused a lot of damage to aircraft and supplies around the base, and they were charged with trying to figure out how to provide advance notice of these types of events in a day and age that's actually characterized by the U.S. Weather Bureau banning the use of the word tornado entirely from forecasts. It was thought to be impossible. And so over 3 days, Fallbush and Miller compiled analyses of previous tornado outbreaks and events in the southern Great Plains to come up with some lists of ingredients that were important for the development of tornadoes, and had the opportunity to test their methods of coming up with these ingredients only 5 days later, when the environment looked favorable for supercells again. And their commanding officer essentially coerced them into saying, will there be tornadoes or not? It wasn't a probabilistic. He said, do we move our resources or do we not? And they eventually said, yes, this looks like a tornado environment. We believe there is risk. And they ended up leaving the office that day thinking their forecast had busted and their jobs were going to be on the line. And then a violent tornado hit the Air Force Base the second time in 5 days due to a storm merger. And it was a mesoscale interaction that ended up producing it, but they were able to accurately predict the environment in which that was supported. And that is effectively what kicked off tornado science. And so I mentioned the forecasting perspective because every advancement in the theory and the modeling has pretty much been tied to the forecasting problem of improving lead time, and improving risk margins and whatnot, and also improving the observational systems to predict them. So this is a really important moment in the history of tornado forecasting. And I also just really like this statement at the top of it that I find a little funny, but the close-knit world of the tornado and severe thunderstorm forecaster often seems somewhat demented to those not knowledgeable in this discipline. This apparent derangement is based on our seemingly ghoulish expressions of joy and satisfaction displayed whenever we verify a tornado forecast. This aberration is not vicious. Tornadoes and open fields make us happier than damaging storms and count just as much for or against us. We beg your indulgence, but point out the sad truism that we rise and fall by the blessed verification numbers. There is a fantastic feeling of accomplishment when the tornado forecast is successful. We are really nice people, but odd. And I can say that that's a pretty good and accurate description of most of meteorology, but definitely the tornado subfield as well. But again, at the end of the day, even in the theory and modeling world, we still rise and fall by the verification on whether or not we're actually able to improve the forecast. So that's I like the statement for that reason.
Can I just ask you if your prior slide suggested that the so-called Miller's rules were formulated in 3 days? Did they elaborate upon them after the second tornado? They must have, right?
Yes. So they
Okay.
after in the years following, is it 1948? Yeah, 1940.
Yeah.
So 1948 to like 1952, roughly, they compiled lots of composites of different cases and things like that. So that's where the Miller diagram starts to come from. And other research. The concept of proximity soundings and whatnot. They really elaborated over the years. This was just the first thing, and I highlight the 3 days because that's how much time they had to essentially compile a local climatology and make a forecast, and it effectively worked. So, but yes, there was more that happened well after that, and it wasn't until 52 or 53 that the U.S. Weather Bureau finally removed the ban of saying the word tornado in forecasts. And, so even in light of their work, it took a long time for them to happen. So jumping ahead a couple decades, we get to the Lemon and Doswell supercell model. There was a previous, this is really a modification to a pre-existing model. I can't remember exactly who the author was, but it was about 4 or 5 years prior of the supercell based off of theory and conceptual stuff, but there was nothing incorporating observations into the concept of the supercell and how its flow should be. And so Lemon and Doswell, in the middle of doing midnight shifts for the severe storms or cells what would precede the Storm Prediction Center, came up with this modified model based using the 57 WSTAR 57 radar data of some supercells, and really identified what I'll call the flank model of supercell flow, and also came up with one of the first theories, or not first, but one of the more concrete theories of tornadogenesis that's still largely held true today, and that the RFD is an important aspect of creating the low-level mesocyclone as well as the tornado. And so you have this rear flank downdraft here, and this forward flank downdraft here, with an updraft in the middle, and that's kind of the main characteristic of the supercell, with the updraft rotating in a cyclonic fashion. And the other interesting thing about this paper is they draw a lot of parallels to mid-latitude synoptic cyclones because of the way this ends up looking. So this is where they began to introduce the concept of baroclinic generation of vorticity in supercells, in spite of not actually having any measurements of the thermodynamic environment in the cold pool and in the warm sector. So they just used the theory to say there should be baroclinicity in generation, but there were no observations of that, just the radar reflectivities. So this would serve as the foundation for them going into field projects like Vortex and Vortex 2, and it was a really crucial paper in supercell dynamics. And then jumping ahead a couple more decades, we get to Markowski and Richardson 2014, where they really start to try and use the numerical power of computers to start simulating tornado genesis at a coarser resolution of 100 meters. You can't actually call it a tornado, but a tornado-like vortex, and where does that vorticity come from? And what's really interesting about their analysis is, one, they focus primarily on how much baroclinicity do you need to generate a tornado, as well as a few other things, and really they found kind of this Goldilocks problem where you can't have a supercell cold pool that's too cold or too warm, and you need some baroclinicity but not too much, because if you have too cold a cold pool, it's harder to lift, but if it's not cold enough, then you don't have baroclinic generation of vortices. That was the primary finding of this, but what's interesting is that the entire paper stands effectively silently in contrast to rear flank downdraft tornado genesis theory, because it doesn't mention a rear flank downdraft being responsible for any of the vertical vorticity that they analyze. And that figure shows some representative trajectories that approach the low-level vorticity maximum, showing that most of them come from along the forward flank downdraft and acquire baroclinic vorticity before being adjusted by the updraft. And so that brings us to where we are now. And then just talking a little bit about the models that we use to do this. It started with Deerdorf in 1970, who pioneered 3D flow filtered Navier-Stokes equations. And essentially, you assume the largest eddies are resolved, and you parameterize the smaller turbulent eddies and assume they're dissipative. And this allows you to hopefully resolve the flow you care about and parameterize the rest of it that may not be important. So the assumption here is that you're resolving the important features. And to close the turbulence part of the equations, Deerdorf implemented first-order closure from Smagorinsky and Willy, and the first time that the LES approach was really used in 3D and storms was Klemp and Wilhelmsen in 1978, where they started to simulate splitting supercell thunderstorms as well as the effect of wind shear on updrafts. So there were like 4 or 5 papers that came out within a 2-year period, and not only or saying here's this method of simulating the storms, but also here are some things that we've found about them. And there were other 3D simulations going on at the time, but the LES framework provided the most flexible and least assumptions when doing cloud modeling. So that's what ended up being the default for up until now, and that's what most people use. Just a selection of LES implementations. The 2 most common ones you'll see are ARPS and CM1. ARPS is developed and maintained by OU, the Center Analysis for Prediction of Storms, and then CM1 by George Bryan at NCAR, but we also have WRF LES and obviously the UW-NMS that all have these abilities to run at large eddy scales of 10 to 100 meters and try to resolve these flows into supercells. So we use CM1, and that's what I'm going to be talking about for the rest of this. So just a little bit about the CM1 configuration. We initialized the model with a horizontally homogeneous base state from a 24 May 2011 proximity sounding to the El Reno, Oklahoma supercell that produced an EF5 tornado in real life. This simulation is 120 kilometers by 120 kilometers by 20 in depth with an inner mesh of 30-meter resolution that eventually relaxes to, I can't remember what the resolution is, but it relaxes to outside the storm to a coarser resolution. But this year we've completed a new simulation that is 10 meters isotropic across the whole domain, same dimensions in the spatial extent, meaning 250 billion grid zones for that simulation. Data saved every model time step. For the 30-meter simulation and every 1/5 of a second for the 10-meter simulation. We use variable lossy compression to be able to store this data, so that means that we do lose some information past the least significant digit that's specified in certain situations, but because it's variable, it only compresses where it feels like it's necessary. So when you specify a minimum accuracy, that's not to say that everything is accurate up to that point. It's the worst case scenario compression. So that means that in gradient, it preserves derivatives in areas where there's large gradients is the idea. And the 10-meter simulation weighs about 1/4 of a petabyte, so that's saved every 1/5 of a second for, I think, 2,000 or 3,000 seconds, somewhere in that range. And I wanted to mention, and what we see in these simulations that's a little bit different from the old RFB tornado genesis stuff is in this animation of vertical vorticity swath that I've got going on here, you really see that tornado genesis looks like an accumulation of vortices that kind of come from the north along the forward flank and some from behind in the interface between the rear flank downdraft and the forward flank. But that's this accumulative process, and there are no large surges or rear flank downdraft swaths that show up in here as being responsible for creating a tornado. So this is more in line with the Markowski-Richardson-Barrett-Clinic generation, and also with this concept of the updraft and the low levels being responsible for driving these processes.
Where is the rear flank? Can you just describe
Yeah,
for
so
those of us
this-
that don't look at these diagrams
Yes,
all the time where
so-
the rear flank downdraft is?
So in this case, I'll go back a little bit right here. So what you're seeing is essentially where that curved line is like this down here right here. If you rotate this by about 45 degrees, it would be the same orientation, I think. So this would be the forward flank right along here where this Barrett-Clinic generation is. This is where the tornado develops, so the updraft would be here. And then this area out here is the edge, the southern edge of the cold pool, and this is where the rear flank downdraft would be happening. And it's a very transient thing. It's not a persistent feature, so you'll get surges of downdrafts in that area. And what I'm pointing out is that there aren't a whole lot of vortices that come or interact from in that region.
What hardware are you running that model on?
We're running this on the Blue Water supercomputer. So that's in Illinois at NCSA, and that's going to be offline at the end of this year. So now we're transitioning, hopefully using Frontera at University of Texas. That's kind of the new NSF supercomputer that's replacing it. I think the 10-meter simulation uses 75% of it. Is that right? So 75% of the entire computer's nodes are in use when doing the 10-meter simulation. We actually blew up a cabinet the other day. An entire 96 nodes exploded. But none of that matters if the simulation doesn't represent reality. So unfortunately with supercells, because of their nature, it is hard to get more than just radar observations. So we really rely on visual representations of the supercell. And this cloud and ice rendering of the supercell is just to show that it passes more than just the squint test. I don't think you have to squint to see that it looks like a realistic supercell thunderstorm. But that's one of the first things that we have to do is just make sure that it's matching or representing reality in some capacity before we can draw any conclusions about it. An interesting feature that shows up in these simulations is what we call the streamwise vorticity current, and it's that this flow along the forward flank downdraft that gets tilted up into the updraft does not seem to interact directly with the tornado, but perhaps supports it through intensifying the low-level mesocyclone. But again, if this doesn't exist in reality, then the simulation probably doesn't hold a whole lot of weight. So I'm happy to say.
What are those lines?
Oh, I'm sorry.
What
That's
is
the
that
vorticity. It's the vorticity magnitude.
Blue guys are anticyclonic and the red guys are cyclonic on the vertical axis.
My apologies. I should have.
Yeah, so.
And the bottom is
blue guy
point.
started out was anticyclonic, the red guy right there is the EF5 tornado.
So the tornado develops in here. You see these accumulations of vortices along the forward flank boundary. Streamwise vorticity current is the larger
Tornadoes
coming
are
on
red.
And the tornado's a bit longer. Yep.
Yeah, so that's the tornado there.
Will they accumulate, but they don't have any impact on the vortex?
So there's a little bit of, so the streamwise vorticity current is really this current of vortices back here that go into the up, but along the front edge you can get these vertical vortices that accumulate. So that will impact the tornado genesis, but not necessarily the whole feature that's behind it and wrapping around the updraft. And then a rear flank downdraft surge happens. So that's what this is right here, and you see kind of warmer perturbations hiding in the vorticity, and that's what kind of wraps and occludes the tornado in there. So that's what a rear flank downdraft surge would kind of look like relative to the tornado. Then you get a counter-rotating anticyclonic vortex, which is pretty common, not super common, but it's definitely observed in that region of the supercell. But the real interesting focus has been on the streamwise vorticity current lately, and there have actually been field projects to go and see if that exists out in reality. And so
you're looking at the vertical vorticity just because that's something that you see a lot of in a tornado. So that's why you're.
this is the total vorticity magnitude, or is this the vertical
total
vorticity?
The total
Yeah, this
vorticity
is the total
magnitude is shaded
vorticity
by the
magnitude.
vertical component. So
Yeah.
the blue guy to the left there is an anticyclonic vortex, and the red ones are cyclonic. So
So it shows you what would be assuming there's a pressure minimum.
I'm just trying to understand the logic behind why we're looking at this.
Yeah, I didn't unfortunately have a whole lot of time to go into the dynamics of it. Basically, what maintains the supercell mesocyclone is this translation of horizontally generated vorticity. So that's this circulation, this broader circulation that you see happening like this with the vortices that's being tilted and stretched into the vertical. So that's why we're taking a look at the vorticity magnitude shaded by its vertical component, so that you can see essentially the nature in which the horizontal vorticity and the individual vortices themselves are being tilted and stretched into the vertical. That makes sense?
Okay, so we're trying to look at tilting and stretching.
Yeah, tilting and stretching, and eventually baroclinic generation. That happens with the horizontal vorticity. So it's just to show the tilting and stretching process happening by the updraft acting on the vortices.
Okay, yeah, I'd have to think a little bit more about how this is shown that.
Okay.
Yeah.
So to mention just the streamwise vorticity current in reality, it doesn't mean anything if it doesn't exist. So other folks have gone out to search for it. There was a field project this year called Taurus, targeted observations, something of supercells. I can't remember the exact thing, but my friend Alex Sheath at Texas Tech goes out with a Ka band radar and scans perpendicular to these kinematic and thermodynamic boundaries to see if there is some sort of circulation that would look like a streamline vorticity current. And so what we're going to be looking at are RHI cross-sections through this kinematic boundary right here. So where the zero isotop is along here is where the streamline vorticity current would be supposed to be, and the RHI cross-sections through that show what is effectively a rotating feature along that baroclinic boundary. We can't say anything about whether or not it's streamwise because of the nature of the radar, but what you want to look at here are the spectrum width plots. You can kind of see these comma head patterns. That would be the easiest way to pick out that rotating circulation. And then you have here the radial velocity along that RHI, and then you can infer a vorticity from that if you assume that the flow is just the flow that's parallel to the radar beam. So it's picking up that there is a solenoidal circulation happening along the boundary, and then the assumption is that in reality there is flow that is perpendicular to this plane. That would indicate that the vorticity is helical or streamwise in nature, and that would be the signature of the streamwise vorticity current. So it's not conclusively a streamwise vorticity current, but Alex is about to submit a paper that shows this both in the radar observations and the simulations. So just kind of driving home that this might be something that does exist in reality, or at least there's encouraging evidence supporting it.
Does the gradient in the radial velocity correspond to the boundary between the cold pool and the overlying warmer air?
I don't know. I know that in this case, yes, the gradient of the velocity is representing that kinematic boundary. You would assume some sort of confluence along the kinematic boundary based off of the flow diagram of a supercell. But in the RHI, I don't know if I could directly tell you based on this RHI exactly where the baroclinic boundary is. It's just assumed from the reflectivity gradient and the presence of this solenoidal circulation that it should be somewhere in that vicinity.
And the reason why I ask that is because especially the middle one of the spectrum it almost looks like a Kelton kind of thing, which would imply a stable boundary of some kind and shear.
Yeah,
and of
so
course you're seeing shear in the radial velocity.
The SPC exists on the cold side of the boundary, so it is somewhat statically stable on that side because you have the cooling effect of the precipitation that creates an inversion. And there's actually other parts of the cold pool where we've seen similar Kelvin-Helmholtz type billows. This is a very strongly sheared case in the lowest level, so it's not too surprising to see that, but it's fairly stationary in horizontal space. And it says still about at the 10 to 12 kilometer mark, so it's not like advancing forward much or anything like that, like a wave would. It's a fairly stationary feature. So this goes into the questions I mentioned earlier about how does the boundary condition and the turbulence closure impact this vorticity that's clearly coming from the lowest 500 meters, kilometer or so. A question I get asked a lot is, why aren't we running with friction? We don't run with friction turned on. And what we use is called a zero stress boundary condition, whereas free slip is a zero stress gradient boundary condition. So what is that difference and why does it matter? How are they applied and how do they affect the generation or destruction of electricity? So to just quickly go through that, this is the momentum equation set as formulated in CM1, and what we're really focusing on are these terms here, which encompass all forms of turbulence in the model. And that turbulence is parameterized by derivatives of the stress, and that stress is a function of the shear strain and the turbulence closure parameter, and that's where you choose your closure scheme such as Smagorinsky or TKE to come up with that value of K, and then that generates through the derivative of stress tensor turbulent momentum tendencies for UV and W. Those turbulent momentum tendencies are particularly sensitive to lower boundary condition for U and V because of this vertical derivative right here. So you get a vertical derivative of K, which means if you have a large change in K, if you have a large change in K, you potentially have a large momentum flux due to the turbulence closure. And so this is kind of supported by some work done by Markowski and Bryan in 2016 to look at the legitimacy of applying friction in LES flows of supercells by looking at laminar flow, because the inflow to a supercell is usually assumed to be laminar in nature. And they tested this by taking laminar flow with the boundary conditions and then introducing eddies into one of them and not introducing eddies into the other. And what they found is that whenever you have no eddies to resolve as such in laminar flow, and you apply a logarithmic friction profile to your lower boundary, you get an artificial increase in order of shear that's an order of magnitude larger than what is predicted by the logarithmic wind profile, and that's because you are resolving no eddies. So what that would look like in this case, so in this case on the right, the figure is of the profile with eddies, and they do some Reynolds averaging to show the impact of the resolved eddies on momentum and shear, and then the impact from the subgrid scale turbulence closure scheme in blue. And what you see is that the eddies are typically being resolved above the boundary, but at the boundary, because you can't ever resolve something perfectly with a hard floor, you have influences from the subgrid scale turbulence closure. When you don't have eddies, it's just that blue line and it's much larger. And so that's the primary reason why it is now not advised to use friction in simulating supercell flows in at least the inflow sense, because the inflow is typically laminar, and if you don't have eddies to do that, so if you want to apply a friction layer, you have to perturb your inflow with random noise to generate eddies, which is how they did this. Additionally, the reason why friction is kind of being looked at in a different light and frowned upon now is that it's based on Mononobukov's similarity theory, and it assumes horizontal homogeneity and stationarity of turbulence, which is not applicable in the outflow of supercell. So we've eliminated the inflow of using a friction boundary condition, and now the outflow is not necessarily a sound place to apply a frictional profile. So the truth is we don't really know how to handle these lower boundary conditions in these models. And I encourage checking out the Markowski 2019 paper to see more about that. They took observations of the cold. Yeah.
So, this is probably naive, but I would have assumed that if you take away friction, you're going to greatly alter the degree of inflow into a tornadic vortex. That with friction, you're going to have a lot of inflow right at the boundary layer. And without it, you're going to have a frictionless vortex that basically sucks onto the surface and doesn't really have a lot of inflow trying to counter the updraft and reduce the pressure gradient. Mm-hmm. So doesn't that change the dynamics of the vortex itself quite a bit?
You'd think so, and that's what confused people a lot and asked why we weren't using friction. Is there's a large thought for a while that you needed friction to generate the tornado in the first place, to generate the radial inflow. And so when the simulation came up with a tornado without using a logarithmic friction profile, that was kind of confusing as what initiated this investigation into what is going on. And it turns out it's because we're not actually using free slip, as I mentioned. We're using a boundary condition where you set the stress at the surface to zero versus in a free slip, you set the stress at the surface to the value above it at the next grid point. So one assumes, so the free slip zero stress gradient assumes there's no horizontal vorticity at the surface is what essentially what you're saying. You're saying that vertical derivative is zero, but the zero strain approach is kind of prescribing horizontal vorticity existing there, and then because of these turbulent momentum fluxes, you're generating convergence through something other than applying friction, is ultimately what's happening. And so that's what I wanted to look at, is exactly that question that you're posing, is kind of what, or at least start to address, is what's happening with that and why does this work whenever we're not running with friction on. And to do that, kind of did two different simulations looking at varying the turbulence closure scheme. So keeping the boundary condition the same, I didn't actually change that. That would be something nice to do in the future, is change the boundary condition. But look at how the turbulence closure scheme changes near the lower boundary and how that's impacting the momentum fluxes. And did that by two simulations at 30-meter resolution, the same as the other stuff. But after the updraft forcing has been turned off, but before the supercells mature, running from a restart file and changing the turbulence closure parameterization from Smagorinsky to TKE to get another storm with some different dynamics and see how that closure is impacting the flow. And so just to look at what I'm referring to with that is some spatial averages of these wind profiles in the lowest 500 meters. I couldn't quite do the Reynolds averaging by the Markowski paper because they weren't actually simulating a supercell, which is horizontally homogeneous noise turbulence. And this, I don't know how you Reynolds average properly certain things about that. So I just did a spatial average showing the mean wind profile in red, and in black is the eddy diffusivity, or that K coefficient that goes with the turbulence closure. And what you see is that it's maximized near the lower boundary, and the lowest really 200 meters, 100 meters, and then tapers off with height. So we're seeing that same thing that Markowski was seeing, where you have maximum influence from subgrid scale turbulence at the bottom with Smagorinsky. But then, if you look at the TKE run in the same area, which these storms, even though different simulations, seem to have very similar characteristics, the turbulence closure is not active at all in the inflow of the supercell. So this is just the nature of how the turbulence schemes are formulated, with TKE being a prognostic equation for turbulent kinetic energy, and Smagorinsky essentially being a closure that says if there's shear, there is turbulence, give a K value. So that's why you don't see that, is this is not shear dependent. There's a buoyancy dependency as well as a shear dependency, but K is effectively zero throughout the entire lowest depth in this simulation. So what impact does that have on the generation of vorticity? And that comes from looking at the vorticity equation. You have this viscous effects term. If you replace del cross F with del cross T, those turbulent tendencies from the momentum equations, that will get you your turbulent generation of vorticity. So to do that, I had to write an entire Lagrangian parcel model from scratch to work on our offline data. If I could just leave this up here for the rest of the presentation, I would, because this has been the last year and a half of my life. So this is really most of what I've done. And now we're finally getting into the ability to analyze the results from that. But essentially, because we save data every model time step in the case of the 30-meter run, we can almost perfectly recreate the trajectories you would get from running with the model in an online sense. So normally people, when they do trajectory work with Supercell, they have to do offline backwards trajectories on data saved about every minute. This is online forward trajectories every model time step. And this is done using GPU accelerators and all sorts of other optimizations that I can put in 500,000 to 1 million parcels, integrate it for 2 hours and only wait 20 minutes. Don't have to rerun the entire simulation to change my trajectories if I mess something up, which happens a lot. So it saves computation, it saves time. It means that we can actually start doing some quantitative analysis of vorticity budgets. So that took a lot of work. That's what this looks like. I just put together a little animation of these trajectories with the buoyancy field underneath, initialized in the region that eventually comes to streamwise vorticity current, and I just colored them by the vertical stretching rate of vertical vorticity. So the stretching term of the divergence acting on vertical vorticity, and the red means it's being stretched, and blue in a positive sense. So increasing the vertical vorticity, and blue means it's either decreasing positive vertical vorticity or increasing negative vorticity, depending on how you look at it. So you see this acceleration upward, there's stretching that happens, and as it reaches kind of the mid-level updraft, it decelerates a little bit, and that's why you see the blues, is that stretching kind of, as it decelerates, it kind of pancakes the vertical vorticity. So we can track these trajectories and integrate the budgets and find out about what's actually happening to create the horizontal vorticity that becomes eventually vertical vorticity and updraft in the tornado.
This is just in the surface layer, right, Kelton? That's why there's
Yeah.
a little stubby telephone pole.
That's, yeah, so these were all in the lowest 200 or 300 meters
Okay.
in this case, starting off, and then they rise up through it. We can initiate the trajectories anywhere. This was just to kind of show that progression of the lower boundary and really the residence time too of how long they sit here, accumulating baroclinic vorticity and interacting with this turbulence at the lower boundary before they ever interact with the updraft. So that's why it's an important part of the question and why I wanted to address it. So first I needed to find a place to put the trajectories and compare the two simulations. So this is a vorticity magnitude volume rendering with the buoyancy field underneath. And just looking at the differences between the two simulations, it becomes pretty clear a good area to target is this vorticity that's being injected by the updraft along the outermost baroclinic zones. That would be kind of this region right here that's a little harder to see, that weaker baroclinicity, whereas the streamwise vorticity current itself exists behind the cold pool. There's this odd inflow feature that's coming along there. So that's where I put the trajectories, because that's one of the bigger differences between the two views. Something that's really fascinating, though, is how similar these simulations are after 2 hours of separate integration with different closure schemes. You still get that same horizontal vortex tube in the back, or both of them, really. The only difference that's major is the magnitude of the vorticity and how far forward the cold pool has progressed. So I just thought that was interesting how similar these were. So releasing those trajectories and tracking all these budgets along them, I initiated them in these locations for the 30-meter Smagorinsky and TKE runs. And this just highlights, one, how low of a layer this is, so 0 to 200 meters, how long it stays in that baroclinic zone, and also that the initial path of these trajectories are effectively the same. So like this section of the trajectory path here is almost the same between the two simulations, but then obviously as it enters this different flow feature, the positions will diverge. So just more focusing on those initial stages when it's interacting with the turbulence. And this is what one of those budgets look like. So the vertical vorticity budget closes perfectly. That's because there are no derivatives of scalar fields like buoyancy and pressure that go into that, or rather those terms are really, really, really small. They are accounted for, but they're really small. And the horizontal budgets match up as well as you can expect for online trajectories, but will never actually match up perfectly because of the nature of the floating point accuracy and the derivative of scalar fields with the vector fields. But I have checked, and the compression is not the reason for the divergence. It has nothing to do with data compression, but a little bit more on that later. What we see is negative horizontal vorticity components increasing with time along these trajectory paths. The same thing for the TKE, except we have a different scale because it requires much more negative horizontal vorticity and much more rapidly as it approaches the updraft. So breaking down one of these budgets, we can look at the individual terms. So these are instantaneous rates over time. So we have the tilting and stretching of horizontal vorticity. So this is looking at one component of the horizontal. And the baroclinic generation, turbulent generation, and the effects of numerical diffusion. And what really stands out here is that while we have baroclinic generation of negative horizontal y-axis vorticity, so generating that streamwise baroclinic vorticity, equal and opposite in magnitude to turbulence closure. And so, and same thing for the numerical diffusion. It kind of changes signs, so I consider that a net, like 0 impact on some of that. But if you integrate these budgets, you're effectively diffusing vorticity at the same magnitude of the baroclinic generation rate. And so that's why that vorticity magnitude in that inflow feature approaching the updraft was more diffuse. It's that it wasn't able to acquire as much vorticity due to that turbulent diffusion. So that's really interesting, and not something that I've seen in any other studies, is that turbulent diffusion is either ignored or assumed to be much, much smaller in magnitude than baroclinic generation. But this says that it's the same order of magnitude. So,
am I reading that wrong? The absolute distance between the blue and the red lines is the same all the way through the 250 seconds, but they have an orientation to the 0 line that doesn't quite mean that at any individual time they're equal.
I'm saying equal in an approximate sense.
Oh, okay,
Yeah,
okay.
they're not,
I
they're
thought
not
you meant-
exactly equal.
Okay.
So like in a order of magnitude sense, they're about the same distance from the zero.
Okay.
Over a long period of time. So that tells you that you've got diffusion acting about at the same rate as the
Okay.
generation,
Yeah.
is what I'm trying to say. Sorry, I should be a little more clear with.
Sorry, we're looking at two plots, and one of them, they're the two different closures, or?
Sorry, no, so this is 0 to 250 seconds.
Oh, I see, it's
So this
zoomed
is
in.
part- So it's that zoomed in of that section right here. That's correct?
Yeah, in your, in your 1 that's 1.5 level closure with TK, do you have turbulence, friction with the ground? Does the ground dissipate the turbulence at all?
Well, so there's no, the only dissipation is gonna come from the set boundary condition that the stress is 0 at the ground. So there's nothing else diffusing anything else other than numerical diffusion. So there's no friction applied. I think a visual illustration that might help a little bit is, you can actually kind of see here in the Smagorinsky, it's like 1/10 of a meter per second, but it's slightly faster at the boundary than it is above it because of this boundary condition. So I don't think there's any diffusion in that frictional sense, if that makes sense. Does that answer your question?
Yeah, I mean, I struggled with what to do with this before, but I think, it seems logical to me that turbulence should dissipate into the ground.
Yeah.
And, it's not in any of these models, you just have zero, they're all zero friction for turbulence, and I think that's important.
No, it absolutely is a important physical aspect of it. I think that the problem right now is that the impact of friction in current simulations should at best be considered a worst case scenario of the impact of friction if you're not perturbing your inflow with turbulent eddies. Now, we could possibly turn on a friction logarithmic profile and perturb our inflow with noise to create eddies and see what that would look like. But that requires a lot of more computation and work than most people are willing to put into that. And so at least the recommendation from Markowski and Richardson was use free slip, but we're not even doing that. So it's got this.
If you do free slip, I would think that would reduce the amount of turbulence at the ground.
Oh, it completely turns off the
Artificial.
T value. The T value goes is basically 0 at the ground.
But that doesn't seem to me to be realistic.
No, it's not.
In reality, turbulence should be higher than that.
So that's the whole reason why I went down this rabbit hole is we know we're doing it wrong. So what is the impact of that wrongness on the dynamics and the budgets? So what is that actually doing? And so in this case, we see with this particular boundary condition, it's diffusing vorticity at the same rate as barophonic generation. But if you apply friction, maybe if you're having the right eddies, it should be much smaller than that. Or maybe that is the right size. I don't know, because we haven't run anything with a friction layer on it yet. But it at least opens up some understanding of what's actually happening because of the choice. It's still not the right choice, but it's better to know what it's doing than it is to kind of be aimless with it, which is where
I think the reason it doesn't actually accumulate, even in reality, at the ground, the reason it doesn't accumulate is because the layer, especially the inflow layer, is fairly well mixed. And you don't accumulate strong profiles of anything in that layer.
Mm-hmm.
And so any kind of a generation of turbulence would be very quickly diffused vertically, so you don't have that kind of gradient.
Mm-hmm.
And I think that's what actually happens. In the NMS, we take care of that because we don't actually use the shear production term to feed KE, TKE. We actually create we create a relationship between turbulence kinetic energy and kinetic energy. So there has to be an explicit transfer, so to the extent the kinetic energy is not decreased, we won't increase the turbulence.
Interesting.
So I think that eliminates a lot of the problems of having friction in that inflow layer to keep it laminar, like you said.
I don't know if this is part of what you're saying too, but one of the other things that was pointed out about applying that logarithmic friction profile is that it's derived over a temporal average of atmospheric profiles, and it says nothing about what the instantaneous momentum tendency due to turbulence would be. So I still don't know how to address that part of the issue either, even when you do apply it or maybe make it less restrictive than the current method is, how you still handle what the turbulence should instantaneously be at any point, since so much of the studies are temporal average or spatial average. And that's, I know Paul Markowski is working on this, and he's looking at the wind engineering community and their boundary conditions and their LESs to see what kind of solutions to the problem they have, but it's very much still an open question. So the goal for me was just to try and understand how it was impacting these simulations. Maybe hopefully if there is a problem, we can identify it and say, this is problematic, but the rest of it isn't, or we don't know if this is problematic, so here's the impact it's having.
I think the things you're seeing there are actually problematic in a lot of places, a lot of other kinds of simulations. Hurricane people, for instance, with the wharf, have huge problems in the boundary layer getting turbulence right. And, you know, there may be some of the same solutions you're talking about.
Yeah. So, yeah, very much an open-ended problem right now, and that's I don't know where to go forward from that, but thankfully there are other smarter people working on it than me. But just in contrast, I'll try and wrap this up real quick. In contrast to the Smagorinsky budgets, what we see in the TKE simulation, where there was no eddy diffusivity or K value in the profile, is there's no turbulent generation of vorticity, or turbulent dissipation of vorticity in the inflow, and also the numerical diffusion is turned off, essentially. So maybe there's something with that as well, but you're effectively allowed to accumulate baroclinic vorticity unhindered as the parcels enter the updraft in the case of TKE, and that's why we see that larger vorticity magnitude reaching out into the inflow, which turns out has an impact on the low-level updraft and intensifying it, because we ran the TKE simulation further, and we get an even stronger tornado than in the Smagorinsky case, because the low-level updraft is also faster in terms of its upward motion because of this lack of diffusion. So I think it's a fairly well-known fact that Smagorinsky is overly diffusive. That's not something that's new, but the vorticity stuff is relatively new, and the fact that it's the same order of magnitude as the baroclinic generation is something that's odd. And if you plot the horizontal vorticity as a vector and show that on the streamlines, some even more bizarre stuff comes up. And I'll be honest, I'm still working on interpreting some of this, but what you have here is you have the velocity vector and the vorticity vector in black and red, and you should only really see the red vector because it's streamwise. You have helical flow, the vorticity and velocity vector are the same, streamwise vorticity, and then in the cyan, you have your vorticity tendency vector due to turbulence, and in the white, you have the vorticity tendency vector due to turbulent momentum. So along with Greg's question about are you diffusing into the ground, I feel like the answer is definitely no when you look at the white arrows, because they're 90 degrees left or to the right of the velocity vector. Friction would act in the opposite direction of the velocity vector. So that's an interesting thing. And because of that, the vorticity tendency vector due to turbulence acts in an anti-streamwise nature to the particle. There's nothing in my mind that says that should be the case. So you're diffusing the vorticity magnitude, but you're not reorienting the vector away from the helical flow component, which is bizarre. There's nothing that says it shouldn't be destroying the helical nature of it as well as the magnitude. So I don't quite know what to do with that. It's only just for one region, but in this particular baroclinic inflow region, it's not changing the vorticity vector's direction, just its magnitude. So that was a really fascinating outcome of that. And got plenty more questions about what that actually means. What if it's the subtle differences from streamwise in this case? Because there are some deviations like here where the magnitude is slightly crosswise from the velocity and vorticity vector. But what if that serves to help reorient the velocity or vorticity vector more into the streamwise direction? I don't know. It's weird, but it's got an impact and it's important and it's there. So just a summary on that gauntlet of turbulence. So we closed the vorticity equation with offline trajectories, which means that we've opened up the ability to do a lot more quantitative analysis of these simulations in terms of how we're acquiring vertical and horizontal vorticity. The choice of the turbulence closure scheme does have an impact on the simulation as well as the boundary condition. The vorticity tendencies due to turbulence appear to act primarily anti-streamwise and approximately opposite in magnitude of the baroclinic generation. The real takeaway is you have to be very careful about near-surface vorticity in supercells and tornado studies, and the truth is none of us are getting it right, so we have to be careful about how we interpret the results down at the lower boundary. which is driving all of the processes that lead to tornadogenesis and maintenance. So that's maybe a little discouraging.
You're certain that all of them are driven by stuff in the boundary layer?
Of all the simulations I've seen and talked to other people in the community doing simulations, yeah, all these source parcels come from 500 meters or lower in the boundary layer that enter the low-level updraft. I mean, you have stuff from higher up that does go into updraft, but it feeds regions of the supercell that aren't as closely knit to the low-level mesocyclone and effectively the seed vortices that become the tornado. And that's also, I haven't showed it, that's also from just some preliminary trajectory analysis of other regions, that seems to be the case, that it comes from that very low level. So some future analysis I'd like to do, need to show quantitatively that the compression doesn't alter these vorticity budgets too much. I've shown it internally to myself by running uncompressed versus compressed, and there was minimal difference, but how much compression can you get away with when doing the simulations and doing these budgets is an important question. I'd like to gather bulk statistics of these different inflow regions, put 100,000 parcels in these different source regions of information and get a bulk statistical analysis of what terms are dominating and driving the processes and where and in what part of the storm's life cycle. Maybe coming up with some objective metrics to compare between multiple simulations, extending this to sensitivity studies. The SVC appears to be responsible for lowering the pressure in the mesocyclone, so doing pressure decomposition of the field, telling us where that lowering pressure is coming from would be helpful. And also starting to look at parcels that actually enter the tornado versus just the low-level mesocyclone. And with that, I will finish and take any questions.
So you've applied your model to what is obviously a very complex system, supercell, with all the roles of baroclinic vorticity and everything else that's going on. What would happen if you applied the same model to something like a subtropical water spout, where you probably don't have a lot of baroclinic vorticity, but you still have to figure out how you're going to get a vortex out of that. And you're probably in the cumulus growing phase where you don't even have much of a downdraft, if any downdraft at all. What do you think you'd see in that case that would explain those vortices?
I think those vortices are more well understood than the supercell tornado stuff, but I'm also, just take this with a grain of salt because it's just from anecdotal memory, but those are primarily driven by convergence, confluence. There's no reason.
Yeah, there's someone who's done this. When you look into them very closely, they're actually quite the same.
They are? Okay. Yeah.
There's baroclinic generation in those as well.
It's just much
Because
smaller.
almost all those water spouts are along convergence lines that have some contrast in temperature.
Okay.
And so there is a generation baroclinically vorticity that feeds into them. And they look, when you get down to the tornado itself, they look almost the same.
What is the source of the baroclinic boundary in this case?
Sea breeze fronts, land breeze fronts.
So if you're out in the middle of the Gulf of Mexico,
You don't normally get
You
water
don't
spouts.
normally get them there. You get them where there's
well, I've seen
some
them there.
thermal contrast, like in the Keys.
Like
Yeah.
even like in Michigan, it's very common along the lake breeze boundary. You'll get water spouts
Yeah.
all the time because of.
Well,
Because
a lot of it really is no friction, there's very little friction in the water, right?
Well, there's friction, not.
But it's much.
But I think the problem, I argue with you about friction being a problem, because I don't have a problem. But what I've done is a little bit weird compared to what everybody else does. And the key to what I do is I generate my turbulence kinetic energy from my loss of kinetic energy. So by making that energetic consistency, I never build up this turbulence kinetic energy in the boundary layer that would destroy things. Because in the model, it actually dissipates vertically very quickly in these well-mixed areas. And so it leaves the flow laminar. It doesn't touch the laminar nature of the flow. So I think a lot of the problems with using friction boil down to inconsistencies in the model formulation and the energetic closure of the model.
Well, it's if anything, it's consistently inconsistent between the other models and how that's handled. But I'd be interested in maybe seeing if we can modify the closure scheme, either the closure scheme or the boundary condition, and test some of these test some of these other scenarios, because all I did was leave the zero strain boundary condition because that's what we're using right now. But you can definitely look at sensitivities using other closures and boundary conditions.
Yeah, I mean, it boils down to the fact that, does the wind slow down as much as the turbulence kinetic energy increases from friction? And the answer is no, it doesn't. And so therefore, all right, what happened? And it's a subgrid scale stuff that you don't see, that any kind of small frictional effects have been just dissipated vertically or mixed out vertically so quickly that it doesn't actually slow the velocity.
No, that's good, because even just taking observations and videos from supercells, you don't see a slow down logarithmic wind
No.
profile in a supercell.
That's right.
If you look at the inflow of a tornado, it's just as fast at like 1 centimeter above the ground as it is 10 meters above the ground. You can see these clouds of
Yeah.
dust translate horizontally, so.
And that's the reason.
yeah.
So when you actually compute the amount of kinetic energy lost, not much is lost in those regions. It's lost somewhere else.
Yeah, so that's at least encouraging that there's a similar idea that friction is being overly diffusive.
Well, I put full friction in, but it doesn't slow the wind down.
Yeah, because of your formula.
Yeah,
Yeah.
yeah, right.
That's what
the
I'm
thing.
saying. So
That's what I'm saying.
No, that's definitely encouraging that there may be ways to apply it though and not have that problem.
You know, and what's interesting about this is this actually solved the problems with the hurricanes. You know, they had the problem, not like you, that they could just say it's free slip, because then you don't get a hurricane, right? You get no equity pumping. So they can't get rid of it. And therefore, when they can't get rid of it, they get screwy boundary layers. So by doing it the way I've done it, I get perfect boundary layers, even with coarse resolution in the vertical. And they don't understand how that can be, but that's how it is. It's just this matching energetics.
I might have a
quotient.
conversation with you next week about
Yeah.
seeing how simple it would be to change how the TKE is
Mhm.
like prescribed to it, and just see how that impacts it.
Ignorant question about this conversation, is that just an accounting trick?
No, it's a closure trick. It's saying that you can't create energy if you didn't lose energy. You have to.
So that's the
energy has to be
constraint, but-
an overall zero-sum process.
How many different ways could you do that with that constraint? That's what I guess I'm asking. Or is that the only way?
Well, I have ways of closing. I say locally, if energy is lost here, it has to be gained here, another process. So I look at the energy budget over the whole thing and then base it that way. But there is a little bit of unknown factors involved there.
Okay.
Where it becomes a little bit hard to say where it is, because it happens on the subgrid scale and over time. So you
Yeah.
have to kind of match things as closely as you can. But
Mhm.
you know the budget, you know how much kinetic energy there was, and you know how much turbulence there was. So
Yeah.
you know those two things, they have to match.
Yeah.
One goes up, the other has to go down. And if you don't make a match, which I'm sure they're not in this, then you have problems.
Yeah, okay.
All I know about the TKE formulation, and I actually need to go through and read the paperwork religiously, but it's the Deardorff formulation.
Yeah, his doesn't match. All the LES people are wrong, by the way.
Kind of a-
I've told them before, I've argued with them about this. They don't understand you can't use the shear production term because it's over specifying the problem.
Yeah,
You
well-
already know your shear production by how much kinetic energy you lost.
That's basically what Smagrinsky shows. It's
Yeah,
just over diffusive.
It may be theoretically correct, but it doesn't match mustard in terms of overall budgets.
Yeah.
So kind of a broad philosophical question. You said that improving the forecasts is what matters.
Mhm.
What's the path between this and improving forecasts?
So, or sorry, you.
What's the sort of path
Yeah.
between figuring out which of these mechanisms is, I guess, the big picture I got, there are two possible mechanisms for where the vorticity comes from,
Mhm.
and you're kind of looking at the relative importance of those two mechanisms in
Yeah, so-
simulations.
Roadmap for this. So going back to earlier, big picture that for my PhD I'm interested in is what helps maintain a long-lived tornado versus a supercell that either has a brief or no tornado at all. So trying to distinguish between not will there be a tornado, but more on this upper end of the long-lived, deadlier kind. So that's the broad forecasting impact would be maybe improving the prediction of these longer-lived tornadoes. But to do that, we need to understand the dynamics of what sustains a long-lived violent tornado in a supercell. And so this turbulence closure process was an investigation of the sensitivities of some of those source regions. So then zooming back out, you would hopefully come up with a theory on tornado maintenance of some sort, saying that these are the processes that maintain the low-level updraft or mesocyclone or tornado. And then you could work outward from, okay, what types of observations do we need to get at that, or what types of modeling improvements do we need to get that? So going with, if we're going to do this operationally, like what they're trying to do with Warren on forecast, provide some sort of guidance on what these sensitivities are in terms of the boundary layer and the source region of how you get a supercell. And then you can work outward long-term towards actual prediction. But right now, it's more focused on, they don't have a theory or a consistent theory for a lot of
Understand the processes so that you can know what to simulate or observe.
Yes.
Is essentially.
And with the efforts with Warren on forecast, they're right now at 1 kilometer resolution for these. But you can there's hypothetically a world in which you could run an ensemble of these idealized simulations initialized from real-world models, and then create an ensemble prediction of tornadoes using this. Let's say 10 years from now we get supercomputers, we can run 10 of these for a supercell ahead of a storm. Then even at this 100 meter to 10 meter resolution scale, we need to know what the problems are there as far as supercell flows go, and so it can advise that aspect of it as well.
Okay, so you're trying to advise future simulations?
Yes, future simulations,
Design and
the
advise.
theoretical under.
Design.
Tornadoes really aren't understood very well. This is just sort of getting at how they work inside these supercells. You gotta understand how something works before you can predict its behavior.
The only simulations of tornadoes previously were chamber studies where you just had a forced top updraft and no interaction with a supercell. So these simulations are really the first of its kind in getting all of the processes of the supercell from birth to death and how that creates and maintains the tornado. So that's where it's different from previous studies, is it's really tying the storm to what's happening with the actual tornado vortex. And so we need to come up with some sort of theory that ties those things together.
Are there any hints yet that there are specific links between the large-scale environment, the observable large-scale environment, and the processes that you're studying on a flying scale?
If anything, it's the opposite. It's not hard to take the same base state sounding and get no tornado at all. It's very chaotic in nature. A compiler, the supercomputer updated its compiler one time, and suddenly a simulation that produced a tornado didn't. It's incredibly sensitive. And so going early, a lot of this was motivated by noticing that at 30 meters, Smagrinsky produced a tornado, but at 15 and 10 meters, TKE closure produced a tornado. So I was really interested in why that was happening, but when we did the run from the restart, where the supercell was establishing its cold pool and then changing the turbulence closure, the drift was much smaller. And so that said that it was essentially chaos in the formation of the cold pools, what I would say for that. So same base state sounding, but all you do is change your turbulence closure, and from T equals 0, you get no tornado at all if you use one closure versus the other. So it's really, really sensitive. Or if you change the numerical, someone else at Texas Tech is doing ensembles of numerical diffusion, turbulence closure, boundary conditions, and initializing them from the same base state, and they're effectively completely different storms. And you can't even compare them because it's apples and oranges.
So maybe they have to be treated fundamentally as a stochastic process.
And that's why I mentioned the ensembles of these things as prediction or even analysis tools for theory. We're trying to work on getting more of these simulations because they are so sensitive to the starting point, what happens with that. So you're not guaranteed to answer your question about the environment, you're not guaranteed a tornado in the same environment. And that actually represents reality. You can have the same environment proximity sounding, and one supercell 40 miles away produces a tornado and the other one doesn't. So it's not too surprising, but definitely makes the problem hard.
What if you telescope out from your simulations, right? I mean, we gotta go, but it's a good conversation, conceptual, philosophical conversation. You telescope out and you just disregard all the tornado differences in your simulation. How far out do you have to go on scale before you realize you've got the same storm no matter what the compiler is, no matter how many ensemble initial conditions you put, so that you can kind of at least parameterize, put a fence around what is necessary to get this supercell? And then the next one is what's necessary to get a tornado on it.
I don't know, but it's a problem I think about a lot. I would love to address I guess what would be considered the intrinsic predictability of this, like at what,
Yeah, I guess that's what it's
at what scales
Yeah.
like where's their convergence of solutions? So a great question is
Yeah,
when you vary
yeah.
these turbulence closures, we're down to 10 meters now. We're resolving not just the large eddies, but the medium and small eddies too. So once you increase your scale and you're not really relying on this turbulence closure, maybe there is a convergence of solution.
Sure.
And so that says something about the scale at which you need to predict these phenomena. and then you can expand that into what the sensitivities to other things. But as far, like, even with the Supercell with 100-meter resolution simulations, you can still get drastically different cold pool structures and temperatures. And we haven't even talked about microphysics. I'm not also going to not talk about microphysics because I'm not a microphysics person, but like that's a whole nother area that's generating this baroclinic gradient, and you know how that at 10 meters, how do you handle microphysics properly? I don't know the answer to that question either. So there's a lot to that. Answering the predictability question would be awesome. Don't quite know how to go about doing that, but it would be a cool thing to do.
All right, everyone, thanks so much for coming up. Let's give Kelton another